The eye head mover spectrum, modeling individual and population head movement tendencies in virtual reality. In VR, gaze shifts are a fundamental part of the user experience. But people don't do this in the same way. Some prefer to move their eyes, keeping their head stable, while others prefer to move their head, even for small shifts. While this behavior has been noted in psychology, it remains largely unexplored in human-computer interaction. Our work addresses this gap by asking 3 questions. How does head contribution to gaze shifts vary between individuals? How prevalent are different tendencies in the population? Are individual tendencies consistent across tasks? Previous metrics had several limitations. First, they oversimplified, reducing continuous strategies into averages or rigid categories. Second, they relied on arbitrary thresholds like head gain or eye-only range, which are hard to interpret. Third, their scope was narrow, often focusing on a single amplitude instead of the full range of eccentricities. And finally, most studies used very small samples, making it difficult to generalize findings to the broader population. To investigate the first 2 questions, we analyzed a large, open dataset of natural gaze shifts from 87 participants watching 360-degree videos. To model individual behavior, we moved beyond old threshold-based metrics and captured the continuous link between head movement and gaze eccentricity. Our solution is the soft hinge model, a simple curve with 3 interpretable parameters: when head movement begins, how gradual the transition is, and the overall contribution at large eccentricities. This continuous approach avoids arbitrary cutoffs, handles sparse data robustly, and creates a uniform basis for comparing people. It also fits user behavior significantly better than prior methods. After modeling individuals, we looked at the whole population. Using functional PCA, we found that almost all variation can be explained by a single axis, from strong eye movers to strong head movers. Each person gets a score on this axis, placing him along a continuous spectrum. The result is clear: people are not split into 2 groups. Instead, most fall in the middle, with some leaning strongly to either side. This spectrum gives us the first real picture of how eye-head coordination varies across a population. Next, we conducted a controlled user study to examine if these tendencies are consistent. Each participant completed 2 tasks in the study. First, the abstract task. At the start of every trial, participants aligned their eyes and head to a central target. Then, a peripheral target appeared at an eccentricity between -50 and +50 degrees, in 5-degree steps. The trial ended once the gaze rested on the target and they confirmed with the controller. Second, the video task, which was a shortened replication of the DSAV 360 free viewing protocol. Participants watched 20 monoscopic 30-second videos, chosen to maximize the number of natural gaze shifts. Each video began from the same central alignment. For both tasks, participants were asked to shift gaze naturally. To analyze the user study, we fit the same soft hinge model to participants' head movements in both the abstract and the video tasks. This gave us a comparable profile for each individual. When we projected these profiles onto the same spectrum, we found a moderate correlation of 0.6 between tasks. This means participants largely kept their relative positions on the spectrum. Even though the context shifted, their individual tendencies remained stable. While tendencies were stable, their expression was modulated by the task context. The abstract task elicited a wide range of strategies, from extreme eye movers to extreme head movers, showing a polarizing effect. The video task compressed behaviors toward the head mover side, indicating that the naturalistic environment encouraged greater head involvement. Our work points directly to applications across VR and AR, from foveated rendering, to interface layouts, to collaborative systems. The key idea is that these designs can adapt to where a user sits on the spectrum, rather than assuming one uniform strategy. And because our model is lightweight, these profiles can be updated dynamically over time. We take the first fundamental step to really understand this behavior. What we show is that the variation we see is not noise, it's a continuous spectrum across the population. That means VR and AR systems shouldn't be built for an average user, but for diversity. And as these technologies move into the mainstream, adapting to this diversity is essential if we want them to be comfortable, accessible, and equitable for everyone. From individual profiles to the population as a whole, our work points toward a more adaptive and more inclusive future for immersive systems.